Geometric Series, an Algebra 2 Pre-Calculus or BC Calculus lesson by Melissa Burkhead. Hi, my name is Melissa Burkhead, and today I'm going to walk you through a geometric series exploration and a few example problems. Let's take a look. Remember, a geometric sequence is a list of numbers in which each subsequent term is obtained by multiplying a common ratio to the current term. So in my first example here, I'm multiplying what number by 1 to get 1/2? I'm multiplying 1/2. And if I multiply 1/2 by 1/2, I get 1/4. And if I multiply 1/4 by 1/2, I get 1/8, and so on. This would be a geometric sequence. The second example, what times 2 equals -6? -3. And if I multiply -3 by -6, I get 18. And if I multiply 18 by -3, I get -54. And if I multiply -54 by -3, I get 162. Both of these are fine examples of geometric sequences. Now we are going to become a little bit more sophisticated in that we're going to work with a geometric series. And right now, let's just consider a geometric series to be a summing of a geometric sequence. So, in these two examples, I'm trying to sum the previous sequences. I wonder if I could find an actual sum, because it does appear that I'm going to infinity. Interesting. When working with geometric series, one often questions, does this series have a finite sum, even if we're going to infinity? Well, we're going to use a geometric example to delve into this question. I'm starting with a square that I've built using geometry software, and I have decided that each side length of the square is 1 unit. Hence, the square's area is 1 unit square. I also have this length r, and notice r can vary from 0 to 1 to a number greater than 1 to a number even less than 0. But let's keep r right here at this time. Now, with this geometry software, I can perform an iteration. And whatever geometry that I've built, I could build that same thing into other points on the plane. So I'm going to start with these 2 points, which were the starter points that I used to create my square. And I'm going to go to an iteration menu, and I'm going to map this point here and this point here. I'm hoping that you see a pattern of squares progress. And that pattern of squares progresses indefinitely. Let's imagine they go to infinity. Well, I definitely see a pattern here as my squares areas, subsequent square areas, are getting smaller. If I were to make R1, I have a set of congruent squares. If I were to make R greater than 1, my squares actually increase in area. If I were to make R between maybe 0 and -1, I get this model. But if I were to make R less than -1, as soon as I do that, I get this model. Interesting things are happening. But let's go back to where we started with this set of squares that definitely have a pattern, a progression. I'm going to also invite some geometric objects to the party so that we can see some similar triangles emerge. We have this triangle with this vertex, this vertex, this vertex is similar to this triangle right there. And I can think about how these side lengths are actually correct. If this length is r and this side length is 1, it should make sense that the distance from this point to this point is 1 minus r. And since we built a square here, each of these side lengths would be r. Now, what if I wanted to find this value x? If I wanted to find that value x, I could say x to r is equal to 1 minus r to 1. Let's look at that proportion. X to r is equal to 1 minus r to 1. And then if we were to use a property of proportions, x would equal r minus r squared. So if this x is equal to r minus r squared, this third square would have side length r minus r, which is 0, and then we take our 0 minus minus r squared, and we get r squared. So this square has side length r squared. 1 r squared. What times 1 equals r? R. What times r equals r squared? R. I wonder what happens as the pattern continues. Lo and behold, we'll notice that this side length is r cubed, this side length is r to the fourth, and the pattern does continue. So now we can think about finding the sum of 1 plus r squared plus r cubed plus r to the fourth, because I'm hoping that you can see this triangle here, this right triangle with this vertex, and this vertex. I'm going to state that that triangle is similar, this triangle right here, this triangle right there, is similar to this triangle right here. Why? Well, if this line is parallel to this angle is congruent to this angle because we would have a set of alternate interior angles, and the triangles both are right triangles. So I think that I can come up with a relationship that states 1 plus r squared plus r cubed plus r to the fourth out to infinity divided by 1 is equal to this 1 divided by 1 minus r. Let's take a look at that proportion. Here I have 1 plus r squared plus r to the third plus r to the fourth out to infinity divided by 1 is equal to 1 divided by 1 minus r. Well, using a property of proportions, that just simplifies to say that the sum of that geometric series is equal to the first term divided by 1 minus r. Now, I bet that we need to put some sort of restriction on r, because when I make my r greater than 1, that sum is not going to be finite. When I make my r between 0 and negative 1, it does appear to be finite. But as soon as I make my r less than negative 1, lo and behold, I do not have a finite sum. So we'll take a look at the formal representation of what a geometric series is. But remember, we have a geometric series because each of my subsequent terms is obtained by multiplying by that common ratio r. So I can find the sum of my geometric series when my r value is between negative 1 and 1. And when we say r is between negative 1 and 1, we are not including negative 1 nor 1. One thing that I tell my students, if you know a geometric series converges where the absolute value of r is less than 1, to find its sum, take the first term and divide that quantity by 1 minus r. This makes you double check your first term. And I'm going to show you some examples on what I mean. First example, We have the sum n equals 0 to infinity of 3/4 to the n. What does that mean? You don't necessarily have to do this each time, but I'm just trying to develop things for you. When n equals 0, we would have 3/4 to the 0, plus, and then we're going to increment by 1, plus 3/4 to the 1, plus, and then I'll go 3/4 to the 2, plus 3/4 to the 3, plus ... Do we see that this is indeed a geometric series where our common ratio here is 3/4, and the magnitude of 3/4 is less than 1, therefore this series is going to converge. This series will converge to my first term, which is 3/4 to the 0, which is 1, divided by 1 minus my common ratio. Now, you can leave things like that, or you might want to simplify. You'd have 1 divided by 4/4 minus 3/4, and that's just 1/4. So this sum is equal to 4. Pretty cool, pretty cool. Let's take a look at our next example. Our next example, we have this 4/3 to the n. Now we're thinking our common ratio is 4/3, right? If we think about our previous example, but let's just write things out. I would have 4/3 to the 0 plus 4/3 to the 1 plus 4/3 to the 2 plus 4/3 to the 3 plus ... We do have a geometric series. Each of our subsequent terms is being multiplied by this r value of 4/3. But wait, the absolute value of 4/3 is 4/3. That's greater than 1. This series does not converge. It diverges. Okay? So, right now we're identifying when we take that 4/3 to the n, that 4/3 is our common ratio. And that common ratio is greater than 1. Let's look at example 3. What's different? Well, I have a coefficient, and then I also have a different start term. My lower limit on summation is 3. Well, what does that imply? I would have 5/6 times the quantity 1/2 to the 3rd, plus I increment by 1. I'd have 5/6 times 1/2 to the 4th, plus 5/6 times 1/2 to the 5th, plus, and then 5/6 times 1/2 to the 6th, plus. Well, I can definitely identify that I have a geometric series. My common ratio is 1/2, and the absolute value of 1/2 is less than 1. So this series is going to converge. And this is a prime example of why I gave you that little note, take the first term divided by 1 minus my r, if you're working with a convergent series. So we can clearly see that our first term is equal to 5/6 times 1/2 to the 3rd divided by 1 minus, and then I look at this. What is my common ratio? What did I multiply this by to get this? 1/2. What did I multiply this by to get this? 1/2. So I would have a 1/2. Now, on the BC Calculus exam, this answer could just be left as such. We could also do a little simplification, but I'm just going to leave it to emphasize that you could leave your answers like this. Let's take a look at this example. I have 7/5 times the quantity 5/3 to the n, and I'm going to sum n equals 1 to infinity. Are you all catching on that my r in this situation is 5/3? We have a geometric series, my r is 5/3. Well, the absolute value of 5/3 is greater than 1. This geometric series diverges. Why? Diverges because r is equal to 5/3, and that's greater than 1. All right? Pretty cool. Pretty cool. Example 5. We have the sum n equals 1 to infinity of pi divided by e to the n. Looks like we have a geometric series, and I really think that I can quickly identify that my r is pi divided by e. But now I need to think, what's the absolute value of pi divided by e? Well, I know pi is approximately 3.14159, and I know my e is approximately 2.71828. Well, that ratio is greater than 1. This geometric series diverges because r is equal to pi eighths, and that's greater than 1. Example 6. Now I'm taking the sum n equals 0 to infinity of e divided by pi to the n. Well, if we were looking at our previous example, our ratio was greater than 1, and e divided by pi is the reciprocal. So, e, remember, is about 2.71828, and pi is approximately 3.14159. So definitely our r is equal to e divided by pi, which is less than 1. So the sum of our geometric series is our first term. When n is equal to 0, my first term is 1, because e divided by pi to the 0 is 1, divided by 1 minus my common ratio. And once again, I'm going to leave it like that. We could make it cleaner, but if you were taking the AP exam, we would encourage you just to not simplify your answers. So let's just remember where we started. We started with a geometric sequence, but then we moved on to a geometric series, and we found instances in which our geometric series would converge. And we developed a formula to find where the geometric series would converge. Finally, we just took it a step further and looked at it in a sophisticated way, where we took a look at summation notation examples and really decided on whether or not this geometric series converged. It's been really fun exploring geometric series with you. Best of luck in your mathematical future.